In computer networks, we are looking at the chapter number 2, the physical layer. Fiber optics. Before we start fiber optics, let me show you a picture. And this is Moore's law. Moore's law shows, or it says, that every 2 years, the number of transistor per chip on a single chip will be doubled. This is the IBM PC. It was in 1981, and this is the present. So the original 1981 IBM PC, it ran at a clock speed of 4.77 megahertz. Mega. Okay, 10 to the power 6 actually. Now today's PC, they have multiple cores, 4 core CPU, and then they are at a speed higher than 3 gigahertz. So you see the comparison, the difference, the increment factor or the increase factor. If you just divide this 3 gigahertz by 4.77 megahertz, you'll get around 2500 times. The same time, the communication link, it went from 45 Mbps, this 45 Mbps I'm talking about a T3 line in the telephone system, to 100 Gbps. So what is the increment factor? Just divide these two, you will get 2000. So the increment in the clock speed and the cores and the increment in the communication speed or the bit rate, the 500 is the difference. And the error rate has also, almost become 0. Now, why the one is 2500, the other is 2000? We are talking about fiber optics, and you will see why this is just 2000, why it has not incremented to the level of the clock speeds. So, fiber optics are used for long haul transmission, that is the long distance transmission in the network backbones, high-speed local area networks, and high-speed internet access to home, fiber to home, FTTX, like this. So fiber optics, there is 100 Gbps. I'll tell you in the end. So an optical transmission system has 3 key components. When we are talking about fiber optics, this is an optical transmission system because it is using a light. So it has major 3 components, key components. The first one will be the light source. The second is actual transmission medium, this one. And the third one is the detector. The detector. The pulse of a light. If there is a light, it will indicate 1 bit. If the light is not there, it is 0 bit. So presence of light is 1 bit. Absence of light is 0 bit. So this is the pulse. The transmission medium is, you see here, it's a very ultra thin fiber of glass, normal glass. So the detector, it will generate an electric pulse because the light is coming. Whenever light strikes on this detector, it will generate an electrical pulse. So light source at one end of optical fiber and the other end will have a detector. So you are getting a unidirectional or simplex data transmission system here. So this system is accepting an electrical signal. First it converts and transmits it in the form of light pulses, and at the other end the reverse happen. That is, it reconverts the output, that is the light pulses, to electrical signal at the receiver end, that is the detector. Okay. So this is how the transmission takes place. Now coming to the physics of fiber optics. Now whenever a light ray passes from one medium to another, there will be certain refraction. Refraction means light will bend depending upon the refractive index or the properties of the two mediums. So it can go away from the perpendicular line of the surface, or it can come near that perpendicular line. Let us take an example of silica, which is glass, and we have the outer area, which is air here. Now the ray is refracted, that is, refraction basically means bending of light rays, and this is bending at the silica oblique air boundary, because the boundary is silica air. So now the density of glass is higher, density of air is lower. So it will bend like this, means bend away. When it goes out from silica to air, it bends away from the perpendicular line. Okay, so beta 1 is higher than alpha 1. In the similar case, if we increase alpha 2, the beta 2 will again increase, again bend. So the amount of this refraction totally depends on the medium. So you can call it as a refraction. The mu. Mu is the index of refraction, refractive index. Now, for certain angle, which is called the critical angle, for a certain angle of incidence, the light will be refracted, but it will be refracted so much that it will come inside the medium from which it was going out. That is, there is a total internal reflection, right? This is called total reflection. At certain angle, the light will not come out of the medium. It will remain inside. So now coming back to our glass or fiber optics, you see here, if there are multiple rays coming, all these rays have different modes. They are bouncing actually. So when they are bouncing, they have different modes. They are bouncing at different angles. So each ray has a different mode. That is why this kind of fiber or this kind of glass fiber is called a multi-mode fiber. Is called a multi-mode fiber. I'll tell you about the microns. This can be used up to 15 kilometer. But if this fiber diameter can be reduced to a few wavelengths of light, that is say 10 microns. As I was telling you, multi-mode fiber is 50 microns. And 1 micron is 10 to the power minus 6 meter. So this is 10 microns. So this is 50 micron, this is 10 micron. That is the wavelength of light figure. So the light will go straight. So fiber or the glass will now act as a waveguide, and the light can easily propagate in a straight line without bouncing like it was happening in the multi-mode fiber. This is called as a single mode fiber. This is called as a single mode fiber. So this single mode fiber can transmit 100 km, 100 Gbps. So this is quite higher, multiple times than the multi-mode fibers. To an extent, it is 50 times higher than the multi-mode fibers. It can transmit 100 Gbps for 100 kilometers. The main thing here to identify here, the optical fibers are made up of glass. This is a glass. And this glass is made from sand. Sand. The sand is everywhere. If you go anywhere, ocean, beach, or even to the desert, you'll get inexpensive raw material, sand. So light, whenever it travels, there will be some losses. That is called the attenuation. That is the signal strength loss. So this attenuation of light through this glass in the fiber optics, it depends on the wavelength of light, lambda, and also the physical properties of glass as well. Attenuation, let me tell you, this is the losing of the signal strength. So it can be through absorption, scattering, dispersion, bending. There are so many optics involved here. So these are the physical properties and of the glass, also the wavelength. Now we always compute the losses in terms of decibel. So in order to do that, we define a ratio of input to the output signal power. So if you assume that Pi is the input power, Po is the output power, so the ratio, we are defining it as the signal power. Now, in order to find out in decimal, we have to use 10 log 10 base 10, 10 into log 10 and pi by po. Pi by po, let us say it is 2. We are saying that a factor of 2 loss of the signal power. What will be the attenuation? Attenuation in the dB is 10 log 10, 2 is pi by po, that is around 3 dB, 3 decibel. So this decibel will be explaining in detail, but right now it's a logarithmic way to measure power ratios. So 3 dB loss of power 2. Now light, when it transmits through the fiber, there are different electromagnetic spectrum we are going to talk about. So let us see here, this is the NIR, near infrared part of the spectrum. This is used in practice. There are 3 wavelength bands that are commonly used at present for the optical communication. The first one is here, 0.85. Second one is 1.30. And third one is 1.55 microns. Microns again 10 to the power minus 6 meter. So all these bands, the width is 25,000 to 30,000 gigahertz. So these are the 3 wavelength band which we use in fiber optics, optical communication. This 0.855 micron band was used first, and the good part was, first, the bad part has higher attenuation loss, but the good part is the lasers and the electronics could be made from the same material, that is the gallium arsenide, though it has higher attenuation signal loss. Now coming to 1.30 and 1.55 microns, these bands have good attenuation property, that is less than 5% if you say 1 kilometer you take. So here you see an example of 1.55 micron band. This is widely used in erbium doped amplifiers. So whenever the light travel, we are talking about fiber. So light pulses, when we sent it through fiber, it spread out its length. Lengthwise they spread. This is the input pulse. So this is the output pulse. So it spreads. And as they propagate, this happens. This is called as chromatic dispersion. Chromatic dispersion. Okay. Now, the amount of this dispersion is wavelength dependent, lambda. But we can do certain things here. I'll talk about solitons. Now this is the ordinary pulse. You see, when you send it through fiber, there will be a chromatic dispersion. You see here also, and in the figure on the left also. Now, if we just send this as a reciprocal of hyperbolic cosine, cos h, 1 by cos h, reciprocal of this is the way, these rays are actually a sin omega type kind of thing. So if you send it as a reciprocal of hyperbolic cosine, it nearly cancels out all the dispersion effects, and this is called as solitons or solitons. So this is how you can avoid and reduce the chromatic dispersion. So there are 2 views in this fiber cables I am showing you. One is the side view of the single fiber. Here we are showing a top view, you can say. Inside a sheath or a protective sheath, there are 3 different fibers. So fiber optic cables, they are almost similar to the coaxial cable, but they don't have the braid, that is the netted braid, protective sheath of the metal and cloth. So the core is surrounded, the center is the core, glass, where the light propagates. And above this core we have, it is surrounded by glass cladding. And the mu, that is the refractive index, is lower than the glass core. Right? Because we want total internal reflection. Then we have the thin plastic jacket to protect the cladding. And then we have these grouping of in the bundles. So fiber are grouped in bundles, and there is an outer protective sheet. That is how it is protected. So I'll just show you a picture here. See, how do we lay these fibers? Because this is an expensive and very, you can say, skilled task. So if it is terrestrial, just lay it down 1 meter. If it is near the seashore, then transoceanic fiber sheets, these are buried in trenches, and there is a special, sea plow which does it. Like this, it looks. This is how in the trenches means a kind of, you can just dig a hole, long hole, and then you can put. In the deep water, they just lie on the bottom. Just lie on the bottom. Fibers can be connected in 3 different ways. So what are the 3 different ways? The first you see in the picture, we can have connectors. So they can terminate in connectors, and that can be plugged into fiber sockets. So these are the connectors I'm talking about. This is the easiest and the best way. Not best way, easiest. I'll tell you why it is not best. Because the connector will lose 10 to 20% of the light. This is very reconfigurable system, easy, but the loss is higher. Second one is they can be spliced mechanically. This is a machine you see also. The mechanical splices lay 2 carefully cut ends next to each other in a sleeve and then clamp them. You can just clamp them. So 10% light loss is there as against 20% in the first one. The third is fusing the 2 fibers together. So 2 pieces of fiber, they are fused and melted to form a solid connection. This is how they are melted. There are certain things also in this. You can get some bubbles, but it will be like seamless connection. A fusion splice is almost as good as a single drawn fiber. So there are 2 kinds of light sources, because light is very important here. All is about light. So there are 2 kinds of light sources for signaling. First is the LED, light emitting diode, and the second one is semiconductor lasers. This is the laser. This is a single mode laser, and this is for gigabit Ethernet long wavelength. Here you see VCSEL, vertical cavity surface emitting laser. Okay, so this is for gigabit Ethernet short wavelength. And the above one, of course, you see the light emitting diode. We have also showed the core and the spot size. So we are not going to the detail of this, just to have an idea. Now they can be tuned in wavelength, because the wavelength has to be tuned, because everything is about light. The total internal reflection, everything is dependent on light. So this they can be tuned in wavelength by inserting certain interferometers. It can be Fabry-Perot or it can be Mach-Zehnder interferometer, and this has to be placed between the source and the fiber. The source and the fiber. So how does it work? The Fabry-Perot interferometer. These are simple resonant cavities consisting of 2 parallel mirrors. You see these two mirrors, 1, 2, and the light is incident perpendicular to the mirrors. And the length of the cavity selects out wavelength that fit inside an integral number of times, m minus 1, m minus 2. So integral number of times. We are not going into the detail again, I am saying just to give you an idea. Then the Mach-Zehnder, it separates lights into 2 beams. You see here a beam splitter. The 2 beams travel slightly different distances, and they are recombined at the end and are in phase for only certain wavelengths which we want to be tuned in. So there are 2, Fabry-Perot and the Mach-Zehnder. These are interferometers. Now the receiving end, what will be there? There has to be a photodiode. So the receiving end of an optical fiber, it consists of a photodiode, and which gives the electric pulse whenever a light strikes it. So the response time of photodiode, which convert the signal from optical to electrical domain, it limits data rates to about 100 Gbps. Okay. Now you know the first discussion we had, why we are limited to 100 Gbps? Because of this. The comparison between fiber optics and copper wire. Fiber have many advantages over copper wire. So the first is, the pictures are also shown here just to have a view. So the fiber can handle much higher bandwidths as against copper. So the bandwidths are higher, 100 Gbps, 100 kilometer, right? So the first one is this. Second one is repeaters are needed only about every 50 kilometer on long lines. Copper we need every 5 kilometer repeater. Repeater is to increase the energy. If the energy is supposed to be losing, we have to increase it. Fiber also one advantage that it is not affected by power surges or electromagnetic interference, even the power failures. But copper does. Fiber is thin and much lighter than copper. And fibers do not leak light and are very difficult for the eavesdropper, etc. It is quite difficult to tap. What are the advantages and disadvantages? Fiber optic, light, more compact. One more advantage is that it can transmit enormous amount of data, 100 km, 100 Gbps, either digital or analog. The external disturbance is well protected by the optical fiber. Less affected. Radars and other signals, this will not cause any kind of disruption in fiber. It has higher bandwidth, as I just showed you. But the disadvantage is the technology. It's very complex transmission and reception. The equipments are very expensive, laying is expensive, and you need skilled people to handle it. Fiber is quite vulnerable to fiber flux as the optical power is higher. Therefore, the optical fiber may also be broken. So fiber flux is a criteria. Splicing, I told you 3 types of splicing are there. So how do you combine them? It can be mechanical splicing, it can be simple connector connection, or it can be melting and joining. These are very complicated and this is very difficult to maintain the splicing wire. And the installation, deployment and then maintenance is an expensive investment and task. Wireless transmission, we are going to take this in the next discussion. Till then, thank you so much. Take care of yourself.